Hello everybody, I'm Sean Parsons and thank you for coming to my presentation today. I will be your guide on this mostly qualitative journey where I hope to demystify quantum mechanics for you. So, without further ado, let's get right into it. So I'd like to start with some historical background. Before the early 1900s, scientific models focused on describing the science of the everyday. That is, scientists worked to make predictions about the natural world that we could perceive with our five senses. Through this understanding, humans were able to create many inventions that would better our lives. As technology developed, though, so did our ability to study much larger and much smaller systems. When we had tried to apply our models to these systems, they failed to make accurate predictions. So now we're caught up to the early 1900s. Einstein started to examine the assumptions of our models that broke for very massive systems, while other scientists did the same for very small systems. While relativity is a fascinating topic in itself, as you know, I'll be focusing on the findings of very small systems that gave birth to quantum mechanics. Therefore, I'd like to talk about the three critical experiments and what classical assumptions they broke. So, the first experiment was blackbody radiation. For reference, a blackbody is matter which can absorb light and then emit it. Light, as Einstein predicted, carries energy. What scientists like Max Planck, who you can see here on screen, is that black bodies could only absorb very specific energies from light, which he called quanta. He concluded that very small systems could only have very specific energies, rather than any energy. This discrete energy idea went against energy being continuous from classical models. This finding was so profound, they named quantum mechanics after Planck's quanta. The implication of this finding turned out to be true for other properties of a system besides energy, like momentum. This is extremely weird, but has been experimentally verified time and time again, just like our next two experiments, the photoelectric effect and the double slit experiment, which showed that all matter has both wave and particle characteristics. Everything around you is both a particle and wave, hence the term wave-particle duality. But you might ask, why don't we notice this wave-particle duality on an everyday scale? The de Broglie equation attempts to answer that question, which is the equation you see on screen right here. This equation relates the wavelength of an object to Planck's constant and the object's momentum and is named after the suave Frenchman you see on screen. Now, if you plug in an average American walking, we get a wavelength so incredibly small that not even our best technology could detect it, let alone any of you could perceive. This explains why we don't see wave-particle duality in our everyday lives. However, when you plug in values for an electron moving through copper, for instance, you get a wavelength that technology can detect and starts to influence how that electron behaves to a significant degree. Scientists needed to incorporate this fact into the new model. So, how would they do this? This is where the oh-so-famous Schrodinger comes in. Schrodinger postulated, which means he assumed to be true without proof, that the behavior of all matter can be described by a mathematical function. You might ask, if his postulates are just an assumption, why does anyone care? Quantum mechanics uses the postulates as a model because doing so makes experimentally verifiable predictions, which is what science is after. He named this function the wave function, and represented it by psi, which you can see on screen. These functions often look like traditional waves, but they don't have to be. If you're wondering what the constants are, they're there to make the argument of the trigonometric and exponential functions unitless as applied math requires, as the sign of a meter, for instance, does not mean anything. This is also the first time we see an imaginary number as the sum of a real and imaginary wave by Euler's formula. Schrödinger asserted that the wave function had to make sense under the physical conditions of the system. Mathematically, this means satisfying boundary conditions, best explained by an example. Here we have the elementary particle in a box where the potential energy is 0 inside the box and infinity outside the box. This means matter can only exist where the potential energy is 0 within the box, as it would take infinite energy to exist where the potential energy is infinity. So our wave function must go to 0 at both ends of the box, which are the boundary conditions. Another postulate was that the wave function contains all observable properties of matter. The question then is, how do we get this information out of the wave function? To do that, I have to introduce a topic called mathematical operators. So, let's give a brief definition of what an operator is. An operator, represented here by the O with a little hat, is a mathematical operation that acts or operates on a function f and returns by a function g. The simplest operator in quantum mechanics is the position operator, which says to just simply multiply f by x. So, if our function is this sign here, then the position operator acting on the sine function would be x times the sine function. Seems easy enough. However, the operators only get more nasty from here, and I've included some on the slide here, as we'll be seeing them on the future slides. To get information out of the wave function, Schrödinger utilized the idea of eigenvalues. I'm guessing most, if not all of you, have taken linear algebra and are familiar with the idea of eigenvalues. If you haven't or need a refresher, eigenvalue problems are where a matrix acts on a vector and returns a constant multiplied by that original vector. If this happens, the vector is called an eigenvector and the constant an eigenvalue. How does this relate to quantum mechanics, though? Well, Schrödinger asserted that there are a special class of operators called Hermitian operators that, when acting on a wave function, produce an eigenvalue. He then asserted that every observable property of matter has a corresponding Hermitian operator that yields an eigenvalue. That is a very loaded statement, so let's try to dissect it. These eigenvalues are the discrete allowed states for a given property. While this idea seems very strange, it's a really clever way to make a new model that accounts for discrete values, thanks to the eigenvalues, and wave-particle duality, thanks to the wave function. As I said before, while strange to us on a macroscopic scale, both discrete allowable values and wave-particle duality are true, so our model needs to reflect that. So, the operators you saw before interrogate the wave function for a given property of the wave function and extract an eigenvalue corresponding to that property. For example, let's look at the wave function for a free particle subject to no potential energy and the momentum operator. The k corresponds to an integer, and the slashed h is Planck's constant we saw before divided by 2 pi. This shows up enough in quantum mechanics that we give it its own little designation called h bar. We let the momentum operator act on the wave function, which brings down an ik by the chain rule, leading upon simplification to h bar k times the original wave function. Therefore, the allowable momentum values for a free particle are an integer multiple of h bar. Again, you might wonder why the momentum operator looks like the way it does. The short answer is because it being the way it is leads to experimentally verifiable results. You can kind of rationalize the I, as it works well to cancel out the I from the chain rule, but that hardly answers for the rest of it. These ideas, perhaps surprisingly, actually lead us directly to the famous Schrödinger equation. I'd be curious if any of you have seen this before, but the most pure form of the Schrödinger equation is actually written as an eigenvalue problem. The Hamiltonian, a sum of the kinetic plus potential energy operators, acts on the wave function to return the total energy times the original wave function, as we saw on the last slide. This specific eigenvalue problem likely gets a special designation as the Schrödinger equation because total energy tells us how matter will behave and interact with other matter, something scientists really want to know. By substituting in what the operators are, This leads to the more familiar differential equation form of the Schrodinger equation. Looking at the Schrodinger equation in this form, it heavily resembles conservation of energy, which you learn about in any elementary physics class. Basically, the Schrodinger equation is conservation of energy that accounts for discrete rather than continuous values and wave-particle duality. Now, I will talk a bit more about what the Schrodinger equation tells us. So as we talked about before, with the particle in the box, there are constraints on the wave function. The Schrodinger equation is so important because it generalizes this concept to any arbitrary constraint and provides a way to solve for the wave function. The form of the Schrodinger equation we saw on the last slide describes what the wave function looks like over space. There is a related equation called the time-dependent Schrodinger equation that describes what the wave function looks like over time. This partial differential equation is even more of a monster to solve, so it's fortunate most experimentalists only care about getting a solution to the wave function over space. This is because the potential energy of an electron around a nucleus does not change over time, and this is the main application of the Schrodinger equation. However, the potential energy does change with space, as predicted by Coulomb's law. With that, I wrap up the heart of my presentation, but because I have some extra time, I'd like to talk about some other properties of the wave function. The first property I'd like to talk about is probability density, also known as the Born rule. Probability density existed before quantum mechanics and was a way to find the probability of an event by integrating under what's called the probability density function. Quantum mechanics adopted this idea by asserting that the probability of finding matter between 2 points is the integral over those points of the modulus of the wave function squared. The probability density is the wave function modulus squared, which we'll remember from complex analysis would be the complex conjugate of the wave function times the wave function itself. You might wonder where this modulus square idea comes from. It actually has an analog in classical mechanics where the intensity of a wave is equal to the amplitude squared. So therefore, the modulus squared idea is a natural consequence of being forced to view matter as having wave-like characteristics. As a result, a less common name for the wave function is the amplitude wave. Another property that follows is the probability of finding the electron over all space must be 1, as this electron must be somewhere. You might notice that the probability of finding the electron at a given spot by setting x1 equal x2 is 0 because you're integrating over a point. Why is this? An explanation lies in what's called the Heisenberg uncertainty principle. So if you've taken a Fourier analysis class, you'll be familiar with the Heisenberg uncertainty principle. The basic idea is that the more you know a function in the time domain, the less certain you can be in the frequency domain, and vice versa. What's intriguing is that quantum mechanics states that position and momentum are Fourier transforms of each other. Therefore, the uncertainty in the position times the uncertainty in the momentum has to be greater than or equal to a constant. This is why the probability of finding an electron at a given spot is 0. This would make the uncertainty in the position go to 0, so the only way that this inequality could hold is an indeterminate form where the uncertainty in the momentum is infinity. The Heisenberg uncertainty principle is again just a natural consequence of being forced to admit wave-particle duality exists. It just naturally comes out of the mathematics of the model, which I hope isn't too mystical. Very quickly, I'd like to fit in one more property. Time to speedrun this explanation. I want to explain Schrodinger's count. Waves can add together to constructively interfere to create a superposition. Each individual wave can have a unique momentum, for instance. The momentum of the superposition wave has the probability of being each of the unique values of the waves it's made up of. However, when observed, the superposition wave will only have a certain momentum. Therefore, the cat is not dead and alive. It has a chance of being alive and a chance of being dead, but you can't tell which until you look at the cat. So that's all, folks. Live me can answer any questions you may have, and I'm sure you have plenty after this, but thanks for coming to my presentation. I hope you enjoyed it. See ya!